Hi, my name is Shrikant, and this project to predict electrical energy output in a combined cycle power plant is a part of ML Foundation for Product Managers course assignment. It's from Duke University on Coursera. Okay, now let's get into the problem. Um, Combined cycle power plant uses a combination of gas turbines, steam turbines, and heat recovery system generators to generate power. And they need to um, forecast the energy output to optimize operations and meet demand. But due to the complexity involved with various units, developing a machine learning model to predict the energy output seems to be a feasible option. Now we have the data set of 9,568 records, and they are the average sensor readings from the combined cycle power plant unit. And it spans over 6 years from 2006 to 2011. And it has the features ambient temperature, ambient pressure, relative humidity, and exhaust vacuum. And we need to predict the energy output. Now, our modeling approach is to understand and pre-process the data first. So we load and visualize the data to assess its quality and identify patterns. And we explore techniques to clean the data, normalize or standardize the data to improve the performance. And we'll divide the data into training and test set. Um, and then we'll explore on regression models, including linear model, ridge, lasso, decision trees, random forest, and gradient boosting. Um, Also, we'll use k-fold cross-validation to utilize the available data more effectively, and we'll regress the trained models with k-fold cross-validation to avoid overfitting. Um, After that, we'll perform model evaluation using metrics like R square and RMSE on the training data set to quantify how well the model is able to predict the output. And the output here is the electrical energy. And then we'll perform the model interpretation. So we identify the best performing model based on high R square and low RMSE metrics on the test data. Also, we'll touch upon feature importance for the prediction, and we'll use some sample data to predict energy output using the best model. Now let's get into the demo. So I have already run this. So we have already gone through all the details. Let's see the step one. So the step one is important helpful library. So we'll import all the helpful libraries here. So basically essential libraries like pandas, numpy, and for visualization, we'll use matplotlib, seaborn, and to process data, we use SK scikit-learning libraries like pre-processing, impute, and model selection. Um, this is for pipelining, for adding data pipelines, and this is to import all the models and the metrics. And the job is to save and load the models. So let's, in this step two, we load and explore the data. So first step is to read CSV using pandas. And then just to view, we can view the sample data. So these are the sample figures. So we have temperature here, volume, pressure, humidity, and the output for these set of features. Let's deep dive into the info, like how many columns are there, how many rows are there, um, that kind of information, what's the data type of those columns and all that information. So we have that information here. And if you want to see the missing values, here we are seeing if there are any missing values. So there are no missing values in here. And let's see here the descriptive data statistics, which are like mean, standard deviation, minimum maximum value, and the percentile data. Um, so basically, for example, this temperature ranges from the minimum 1.81 to max 37. So from this, we can see when temperature is minimum. Okay. From this, we can't figure out anything. So let's see how the data distribution is visually. So we can use histograms to visualize the data. So this is how the data is. Um, so we can see that there are few records with the temperature less than 5, and there are few records with temperature less than 33, but most of these are between temperature 10 and 30. There is lots of data. Um, and similarly, we have left skewed data here, and then right skewed data here. Um, And then the next thing that we need to check is the outliers. So let's see if there are any outliers in the data. We can use box plot using SNS library to see if there are any outliers. You can see that there are some outliers here in humidity and the pressure. There are some outliers here. Um, and now let's further explore and find if there are any correlations within the features or within the feature and the output variable, which is the energy. So we can generate the heat map here for the correlation matrix. And then if you see the temperature seems to be positively correlated with volume and negatively correlated with energy here. Um, now, now that we have some very good understanding of the data, let's step into the data preparation part of it. So these are just the basic functions to get the numerical categorical features. Um, so so here, we are splitting the data into the features and the target. So all the features will go into X, and all the target will go into Y, and we'll split the data further into training and test data. We'll use the training data to evaluate the models, and once we find the best model, we'll use that model and test it using the test data. Um, and this is the function for outliers. Um, and here we are using this pipeline wherein we are using the roboscaler that we mentioned in our approach. So roboscaler helps to treat outliers. It's robust to outliers. Since we have the outliers, we are using this roboscaler, and this is the pipeline that we can use. Um, so here we are removing the outliers using the quantile method IQR, and the treatment is cap. We are capping the value. Um, and after treating with outliers and performing and applying feature scaling using roboscaler method, this is how the data looks. So from the numbers, this is how the data looks after scaling, and the train data and test data. Visually, if you want to see, this is how it looks in the box plot. So now we can clearly see that there are no outliers and the data looks um, like symmetric here rather than asymmetric um, here. So it was all over the place. But like now, after applying scaling and removing outliers, it looks like this. And now let's get into the model building part. So here we are defining all the models that we need. So linear regression, ridge, lasso, decision trees, random forest, gradient boosting, etc. And then we are using this k-fold cross validation with 5 splits here. Um, and this is where we are evaluating the model. So we are further splitting the train into basically the training and test data. Um, and here, this is where we are fitting the model and we are getting the predictions and we are getting the metrics, RMSE and R2 here. Um, and the results are saved, the metrics results are saved in the result data structure, and we are saving the model into joblib. So all the models are being saved here, the decision tree model, gradient boosting. So the models that we are saving here, we can pick them later. Once we find the best model based on the metrics, we can pick them and use that model to test on our to test using the test data. Um, so step 5 is model evaluation. So here we are extracting the model names and mean RMSE score. So if you see the model comparison by mean R2, so we can see that linear regression is 93%, the ridge also same, lasso is bit down, decision tree is 92%, and random forest seems to be the best, it's 96%, and gradient boosting is 95%, just 0.1% lagging. And if we use the other metric, RMSE, we can see we have to find the lowest RMSE. So regression is 4.57, ridge and lasso is a bit more, decision tree is 4.69, and random forest is again less, 3.46. So based on these metrics, it looks like random forest is the best model so far. So now we can conclude from our experiments that random forest is a better model based on these statistics. And then random forest model. So what we're doing is, so the saved model, so we have saved all the models here and we're picking the random forest model and then we are predicting on the test data. And if we see R score, R2 score, it's 94, which is close to what we have in the what we have from the training data, and root mean is also close to what we have in the training data. So it looks good. It's not overfitting. So this seems to be the best model as of now. And now let's get into the feature importance. So there are 4 features, and which feature is contributing for the output? To predict the output, we can get from this information. So the same thing here. So it gets saved under feature importance. So we are getting that. And if we plot that, we can see the decision tree, random forest, and gradient boosting all say that AT, which is the ambient temperature, and V, the volume, are the 2 main features that are contributing to predict the energy. The pressure and humidity are also contributing, but it's less. So in the next experiment, we can only use these 2 features, and then we can predict the output and see how it goes. But for now, random forest seems to be the best with all the 4 features. Now let's do some data prediction here. So we are just adding new columns, some new data here, sample data, and then we have to perform the same thing that we did earlier. So we are removing the outliers from the new data, and we are applying the pipeline, basically the scale, we are scaling the data here, scaling the new data, and then we are using random forest model to predict the outputs, and we can see the outputs here. So when the temperature is high, so if you see when the temperature is low here and the temperature is high here, so when the temperature is low, the output is high, and the temperature is high, the energy output is low. Um, so that means, as per the correlation matrix, the negative correlation of temperature and output is being seen here as well. So it looks like it's a good model. So that's it for the demo. And then now let's quickly summarize what we have done. So we have seen the data, we have around 9,000 records, and then we have looked into the features, and we need to predict the output, and we have explored the data. We have seen the correlation, outliers, and then um, we have split that, we have divided the data using 80-20 split, and we have handled the outliers, and we have scaled the features, and we have done model building with various models, and we have used cross validation and evaluated the models based on R-square RMSE. And model selection, we have found that RMSE MOs are the best model, and then we have demonstrated the model's ability to predict the energy output for the new input data. And I think that's it for now. And thank you for your time.